Hi everyone, let's talk about this fun speed cubing visualization I made. What do the points mean? What are the axes? And most importantly, what do the orange and blue regions signify? We'll get to all of that soon. I was recently at Rubik's WCA North American Championships in Toronto, and it was awesome meeting so many of you cool people there. Now, if you watched the final 3x3 round of that competition, whether in person or via live stream, you may have seen this interesting orange and blue scatter plot show up on the projector every now and then, between competitors' solves. As you can guess, that's the visualization I made, which you can experiment with yourself at htwins.net/hthplotter. This video will help explain what information it's actually portraying. If you only want to see the tutorial on how to use this, go to the timestamps 8:37 to 11:30.
Part 1. My initial motivation.
So let me explain my initial motivation for doing this project. Okay, as many of you know, the standard way that most speed cubing competitions rank their competitors is by having the competitor do 5 timed solves, and then we exclude the slowest one and the fastest one, and then average the middle 3. In this case, it would be 6.98. And this is to safeguard against outliers of competitors completely messing up solves by having pieces pop out and they spend minutes trying to fix it, or extremely lucky solves with skips that give competitors times way below what they actually average. A whole bunch of official and unofficial competitions run this way. So what does this mean? Let's look at Laser Monkey's Monkey League Season 1 as an example. If there are 2 finalists, in this case Leo and Bill, who have each completed 4 of their 5 solves, and they're sort of waiting on the 5th, as the audience, we would like to know, what do each of the competitors need to win or lose the entire round and essentially the entire competition? When you have 4 results already in the database, it sort of limits what you could possibly get as a final average, because your average will either consist of A, the 3 slowest times of those 4, B, the 3 fastest times of those 4, or C, the middle 2 times of that 4, along with the 5th time if it lands somewhere in the middle. So looking at Leo's times, given that none of them are below 5 seconds, there's no way, no matter what happens, that Leo will ever get an average below 5 for this round. And in the same way, since all of Leo's times are below 7, there's no way that Leo's average for this round will be above 7 seconds. And of course, there are tighter limitations than that, but that's the general idea. So up until now, when competition organizers want to give the audience an idea of who is best poised to win the competition, they use this thing called best possible average, or BPA, to sort of judge who's doing better, who's doing worse, who's got the lead, who's got the handicap, and so on. But this is far from the whole picture, and I'll soon explain why, but also no shade to Laser Monkey, I love you Philip. The Monkey League doesn't even use averages of 5 anymore, so it doesn't matter. Anyway, why is best possible average not painting the full picture? Let's look at a hypothetical. Suppose the competition comes down to 2 competitors who could win the whole thing. Competitor A, who I'll write in green, and competitor B, who I'll write in purple. At this point, each of them have already completed 4 of their 5 final round solves. Competitor A is not that consistent and has gotten times of 5.00, 6.00, 7.00, and 8.00. Competitor B is much more consistent, always getting low 6s, so they've got 6.20, 6.30, 6.40, and 6.50. And they haven't done their 5th solve of the round yet, and we as the audience want to know who's more likely to win. So if we look at competitor A first, if their final solve is at 5.0 seconds or lower, then the middle 3 solves of their average will be these 3, essentially the fastest 3 of the first 4. 5.00, 6.00, and 7.00, so their best possible average will be 6.00 seconds. By the way, using similar logic, their worst possible average is the average of their slowest 3 times of the first 4. So we could write that their worst possible average, or WPA, is 7.00, although I haven't seen any competitions use WPA as a stat. Let's put a box around this. By the way, if a competitor's 5th time is between the extremes of their first 4, then their final score will be the average of the middle 2 of the first 4 and the 5th solve. So if the 5th solve is 6.25, then the average is 6.42. Using the same exact process for competitor B, if competitor B's 5th solve is 6.20 or better, their final score will be the average of the middle 3 solves, which will be the fastest 3 of the first 4. And in this case, that's 6.30. So their BPA is 6.30. And using similar logic, their worst possible average is the average of these 3 guys, which is 6.40. So Only going by the BPA, it looks like competitor A has a better chance of winning than competitor B because their BPA of 6.0 is much better than competitor B's BPA of 6.30. But if you look at the distribution of these times, what you can see is that no matter how competitor B does, either getting a world record of 3.47 or taking 10 minutes to solve the cube, their average is pretty solidly going to be 6.3 something or 6.40, a very tight range. So really, the entirety of the outcome of this competition depends on how competitor A does. If their fifth solve is really fast, like a 5 or better, then their average will end up being a low 6, and no matter what competitor B does, they'll lose. But if competitor A's final time is really slow, like a 7, 8, or like 10 minutes, then their average is going to be a high 6 or worse, and it really doesn't matter what competitor B does. They're going to win no matter what because their worst possible outcome is still better than that. So what does this tell us? Well, it tells us that by just looking at BPA, it gives us an incomplete picture to falsely think that, oh, competitor A just has an advantage over competitor B, when the real picture is something more complicated where somehow competitor A's score just has a lot more weight in determining the competition than competitor B. And this whole discussion we've been having is just the introduction for why I created this.
Part 2. Explaining the 2D grid.
So what is the idea behind my head-to-head average of 5 plotter? Well, if we go back to a hypothetical where we have two competitors who have each done 4 solves, we essentially have two unknown variables, how each of the competitors are going to do for their final time. We can call those unknowns x and y, and whatever x and y's true values come out to be will affect the result of the competition. Essentially, x and y's value entirely determines who wins. So we're kind of going from a place of r squared, like 2 dimensions of real values, to a yes or no question, basically. I don't really know how to describe that. So you might see where I'm going with this. Imagine we create a 2-dimensional Cartesian plane where the time that competitor A gets for their 5th solve determines the x-coordinate, and the time that competitor B gets for their 5th solve determines the y-coordinate. And of course, both of these are going to be measured in seconds. So what this means is that the combination of both 5th solve results corresponds to 1 point on this 2D grid. For example, if competitor A finally goes up to compete and gets a 6.01, and competitor B goes up to compete and gets a 9.01, all the information about those two solves can be represented by the single point of 6.01, 9.01, represented with this point and the coordinates as I just described. So in a way, this grid is basically representing the entire space of possible outcomes for the 5th solves. Rewinding a bit though, we actually don't know what they're going to get for the 5th solves before they happen, so we have to erase this. What if we had an all-knowing computer program that could look into all possible futures and basically draw a boundary on this grid, whatever it may be, color one side one color, and color the other side the other color, and the computer says to us mere mortals, go ahead and do your 5th solves, which will correspond with a point on this grid. Whatever color that point lands on will tell you who wins the round. And the computer is always correct, so this boundary basically tells us everything we need to know. Well, spoiler alert, as you can probably guess, this computer program is this tool that I made. I basically just explained the general idea of HTH plotter.
Part 3. How to use the plotter.
So finally, here's how you use it. First, click on Name 1 and Name 2 to enter in the names of your competitors. I'll just use Max and Timon as an example. And for this entire graph, Max will be represented with the orange color, and Timon will be represented with the blue color. Similarly, Max's times will always be represented with the x-axis going rightward, and Timon's times will be represented with the y-axis going upwards. So for the first solve, if I were to type that Max got a 4.5 and Timon got a 6.5, you can see that on this coordinate grid, in order to get to the point representing solve 1, we have to move 4.5 units to the right to represent Max getting 4.5 seconds on that scramble. And then we have to move 6.5 points up to represent Timon getting 6.5 on the same scramble. And as a quick reminder, the information about both Max and Timon's solve 1s are fully encapsulated in this single point. So then for the second solve, suppose Max gets, say, a 5.8, and Timon gets a 5.1, we will have a second point, which is located by moving 5.8 units to the right for Max and 5.1 units up for Timon. The location of these points compared to this y equals x line basically tells you which competitor did it faster. And it's basically the same deal for solves 3 and 4. Also, if you prefer, you can press space on this website to have it manually time your solves. So this is Max solving and 1, 2, 3 seconds are going by and then he's done. And then we press space again to start timing Timon, and that's where the point will start moving up because Timon's solves are represented with the y-axis. We hit space again to stop it. We can't get much information about who's going to win the entire average until both competitors have finished their 4th solve. So let's say we hit space to start Max's time, and he gets a slightly slower time than average, perhaps 7 seconds, so let's just wait until it gets to 7. And then he's done, and then Timon goes. Okay, ignore what's going on now, but when he hits space, this basically represents when both competitors have finished 4 solves and are each just waiting to finish their 5th solve. And this is the situation I was talking about in all my hypotheticals. You can see that the all-knowing computer program that I referenced earlier has drawn a boundary, this white dotted line that I'm following right here with my mouse. And you can see that it's colored both sides of that boundary with the colors orange representing Max winning the average and blue representing Timon winning the average. If the 5th point lands in the orange region, Max claims the average, he wins, hands down. If the point lands in the blue region, then Timon wins the average, hands down. If that 5th point happens to just coincidentally land in any of these white regions, then we get an exact tie. The averages will be the same. I did not account for the fact that when 2 competitors get the same average, by WCA regulations, the one with the faster single wins. Right now, the white line just means they got the exact same average.
Part 4. Testing an example.
But anyway, let's see an example in action. So Max starts first and the timer is going. Let's say he gets a pretty typical time of maybe 6 seconds, like that. And from right here, you can see that when Timon starts his timer and it moves up, he will win the average up until the timer crosses about the 4.75 area. And then it flips into orange territory where Max will win. And you can actually see some statistics written here in text. But just watching it visually, as the timer's going up, if Timon were to finish now, it's blue, he'd win. He'd still win, but then it crosses over, Max would win here. And as the run is finished and all 10 solves are completed, you can see that the 5th point, this X, is in the orange region, which means that Max has won. And if you actually look at the numbers, Max has an average of 5.46, and Timon has an average of 5.85. Timon also somehow has a world record single. That doesn't really matter though, so Max has won. So that's the general idea. I think you should be able to use this on your own if you want to now, but here's some other points to consider.
Part 5. Interpreting the plot.
The first 4 solves of both averages are what determine the coloring of this graph. The fact that we have this sort of S shape where it's like horizontal, then diagonal, then horizontal, is fully defined by the first 4 solves of both competitors. The 5th solves will never change the coloring by definition. By the time they start, the coloring is already set in stone, and those 5th solves only determine where that X lands on that coloring. It's sort of like the first 4 solves create a treasure map, and then the 5th solves tell us where on that treasure map we are. Another point is that if we rewind a bit so that the 5th solves haven't been done yet, we can get some helpful information about where the 2 competitors stand just by looking at this curve, and that's information we would not get just by looking at best possible average. So what do I mean by this? Well, if we look at the Timon axis, everything above y equals about 5.8 is orange. So this means that if Timon gets a time slower than 5.82, it doesn't matter what in the world Max gets for his final solve. Timon is going to lose. For example, if Timon has a 6.01 and Max has a 0.01, Max has won the average. But if Max has an extremely slow 59.01, he still wins the average because the X is still in his orange region. Similarly, everything below the y equals 3 line is blue. So this means that if Timon thinks that, for whatever reason, he can secure a sub 3 for his final solve, it doesn't matter what in the world Max gets for his 5th solve either. Timon has secured a victory. For example, if Timon gets a 2.50, then if Max gets an extremely slow 59.01, then of course Timon wins the average. But even if Max gets an extremely fast 0.01 second solve, Timon still wins the average because the X is still in his blue region. It's only in this middle region between 3 and 5.8 that Max's times even matter.
Part 6. Where do these curves come from?
So now that I've covered the basics, it can be fun to just spam space and see what sort of curves you get. Like that. But this can lead us to the question, where do these curves come from and why are they shaped the way they are? Now, if you just want to use this tool to get your information, you can leave this question entirely unanswered. But if you're interested about math, let's look into it. I'm going to move really fast through this part because not many people need to know it. So first, consider what would happen if we did not exclude the fastest and slowest times. So in this example, let's say that A has 1, 3, 5, 7 so far, and B has 2, 4, 6, 8, and we're just taking an average of all 5 times. Well, an average of all 5 times is just 1/5 of the sum of 5 times. And winning the sum means you've won the average, so they're synonymous. What this basically means is that we're just summing up this guy and this guy and this guy and this guy. In this example, B's sum of times is 4 higher than A's sum of times, which just means that B sort of has a 4-second handicap going into the final round. And what this means is that the boundary line for this type of average will just be a shifted version of y equals x. It will be y equals x minus 4, which is really boring. Okay, done with that. So what happens in the real world example where we are getting rid of the fastest and slowest times? Well, I want you to look at this graph, which you've already seen many times, and imagine drawing a bounding rectangle containing the 4 points that already exist. Inside this bound is where the 5th solve will count for both players. And because the 5th solve is counting for both players, that makes this situation analogous to what we saw earlier, where we aren't excluding the fastest and slowest times. And in that situation, we just get a shifted version of the y equals x line. So this is like y equals x plus 5 or so, but it could be any constant, right? Basically x plus b. And the reason why this is the same is because the offset or handicap that both players are experiencing while we're in this region are held constant throughout this rectangle. So whether we're here or we move here or wherever we are in here, player B is the same number of seconds behind player A with their sum. By the way, ignore the aliasing of the white jagged line. Like the fact we get these weird squares instead of a nice smooth line has to do with rounding. And right now we're not going to talk about that. Now, if your view of the entire world was just this rectangle, like this was your TV screen, this would be a very boring view because you have a single diagonal line with no kinks. But what is happening at the boundary of this rectangle? Well, if you imagine yourself being near the northern border of the rectangle and then wandering around randomly until you cross that northern border, what's going to happen? Well, as soon as you cross that upper border, that means that player B, in this case Michael, has gotten a 5th time that is now slower than the slowest time of their first 4. In this case, slower than 0.94. And what does this mean? This means that Michael's 5th time is not going to count in his final average. So whether that final time is 0.95, barely the slowest time, or it's something like 35.89, some ridiculously slow time, it is not going to affect his score at all. So no matter how far you move up, you will see the exact same slice of the universe. It's sort of like you take the selection tool and select the uppermost sliver of the TV screen and then scale it up to infinity. It's a similar deal with the left side. If you're a dot near the left border of the rectangle and you start wandering around randomly and then you suddenly cross the left border, what's happening is that player A, or Carrie in this case, his 5th time is now becoming faster than all 5 previous times because, you know, all 5 times are in the rectangle. So his 5th time is not going to count because it's too fast. And no matter how fast that time gets, his average is going to stay the same. So it's the same deal where you basically select the leftmost sliver of the TV and stretch it out to infinity like that, except it won't have all these weird markings on it. And that actually also happens for the bottom side and the right side. It's just that in this example, there's nothing interesting happening on the bottom or right, so you can't see the weird stretching effect that's happening here or here. That explains why there are these kinks in the rectangle. But then what's fun to think about is how many basic types of curves are there?
Part 7. How many types of curves are there?
From experience, we've already seen an S shape where the line is horizontal on both sides, and we've also sort of seen a C shape where the line has a vertical and a horizontal section. And as we sort of let Michael's 4th time go up, we can see it sort of evolving between a few of them, right? It goes a little fast, but you can see it's sort of evolving from one curve to the other. How can we count how many types there are? Well, it's actually kind of fun because in any of these graphs, we will have that bounding rectangle around the 4 original solves of the competitors. And then we have the shifted y equals x line somewhere in there, and wherever it hits the edge, it just shoots out orthogonally to infinity. So really, the question of how many curves are there just becomes a question of how many ways can this arrangement happen? And it's really easy to count. There's only 6. So there's the case where our bounding box is a tall rectangle, and then the line hits it at such a way so that it comes out horizontally on both sides. And this was the case in that first example with Max and Timon, where Max's times didn't matter if Timon did really, really well or really, really poorly. And for every case we find, there's another case for when we swap the x and y axes. So for this vertical rectangle, we can switch it into a horizontal rectangle and get a line that looks like this. Well, if we want to recreate this shape, we just need to create a situation where player A, or the horizontal axis, has a very wide spread between their fastest and fourth fastest times of their first 4 solves. And player B, the vertical axis, must have a very narrow range between their first 4 solves. Then we just have to fidget around with the numbers a little bit to get the identity line shifted so that it hits both the top and bottom. So I'll call player A the wild card because they're the one who has to have a very wide spread between their slowest and fastest times. And then I'll call player B consistent because they need to have very narrow range. For wild card, I'll say they get a 5, an 8, a 13, and a 16. And for consistent, they're gonna get around 10 seconds every single time. So like 9.95, maybe like 10.30, maybe they get a 9.7, and then they get a, let's say 10.9. And there we go. We get the exact shape that I was showing you on MS Paint, but in the real world. So there we go. These are 2 different possible curves. And then the other 2 situations are just where the rectangle is kind of whatever, but the diagonal line hits one vertical edge and one horizontal edge, resulting in what I like to call a C shape. That doesn't really look like a C, but you get the idea. And then the same deal when we switch the x and y axes, there's the curve coming from the other side. So these are 4 of the curves, and then the last 2 curves are just where one player is so much faster than the other with their first 4 solves that they just completely blow out the entire screen. Like imagine if player A, who we'll call slow, has all times above 10 seconds. And then player B, who I'm going to call fast, has all times below 10 seconds. You can see that there's no way for the slow competitor to beat the fast competitor, because the slow competitor's best possible average is the average of their 3 fastest times, which is 13, and that is still slower than the fast competitor's worst possible average, which is about 5.3 or something. But what you can think of these cases as is that the bounding box rectangle is just so far away from the shifted identity line, like this, that they never touch. And the entirety of the rectangle is, say, within the blue side, and the other side is orange, but it just never gets seen. So because this is all blue here, the rectangle stays blue. And same with the other rectangle, but in the other direction. That answers the question. Ignoring ties, there are 6 possible curves. With ties, I think there's 14. I'm not going to show them all now, and you can do that as a puzzle for yourself. But here's an example of one of those tied cases. And this happens when the shifted identity line hits a corner close enough that the entire stretched corner of the bounding box contains the tie region, extending that tie region to infinity.
Part 8. The plotter's origin story.
Okay, so that was a lot of talk about the math behind these curves, but now it's time for real world talk. So creating some applet like this was a very nebulous idea in my head for the past year or so. It really intrigued me because I really had no idea what these curves would look like. So it was more of a curiosity of what could they possibly look like if I made the tool happen. But then when I realized that North American Championships was coming up and I still hadn't made the tool, I was thinking maybe I should try to make the tool before I go, because then I could show it off to friends when I'm there. But the date of the flight was just arriving too quickly, so I was like, I'll just wait. No one's really asking for this, so I'm not going to do it. But then I got an email saying that my flight had been delayed for 2 hours, so I thought that was a sign from the universe that I should spend those 2 hours to start coding a prototype of the tool, which I did, but I did not finish because it was a lot more work than I thought, and the math was actually a lot more difficult than I was anticipating. So what I did was, on the 5-hour plane ride from San Francisco to Toronto, I basically coded this on the plane because I realized I didn't really need internet connection to test this. You know, it's just a simple HTML file. What was difficult was that this is made with JavaScript on the canvas, and sometimes there would be a JavaScript function that I kind of forgot how to use, and it was a weird feeling that I couldn't just Google the documentation for a function I hadn't used for a while. So it was just sort of like coding as if you're in an underground bunker with no resources.
Part 9. Minimum viable product.
I really want to make it clear that this was a minimum viable product that I was only making for my own personal use, sort of as a curiosity, like what could these shapes possibly look like. What I did not anticipate happening was that as I was coding this tool in the venue for North American Championships, a bunch of people would see it and we'd start conversation, and some of the people who saw it were Keaton Ellis and Mitchell Lane, who I'm really grateful for because they're the ones who are like, that looks really cool. Let's see if we can get it on the big screen projected by 3x3 finals on day 4 of the competition. So I actually spent maybe half of my competition time at the venue tables coding this because I wanted to get a minimum viable product out by the time finals round came around. So this sort of felt like a hackathon where I had a very limited amount of time and I wasn't trying to cover all edge cases or make this user friendly. I was just trying to get anything that worked out there so that people could at least understand the concept. But the thing is, it's not very self-explanatory. So I do understand that, there are about 1,500 people watching the finals round of this competition, including in person and virtually through live stream. And for the vast majority of these people, they had no explanation of what was popping up on their live stream after each competitor's fourth solves. So I do understand that for those people, seeing this confused them and they might have liked more explanation, but I do feel like I couldn't have really mustered anything better than what I got given the limited circumstances.
Part 10. The plan going forward.
And I think my plan going forward is just to make the source code for this tool open source on GitHub so that everyone can see what I did and how I did it. And then I don't plan on developing this further aside from very minor bug fixes. So if anyone wants to see a new feature added or the UI overhauled, now that it's open source, you can be the change you want to see in the world, right? Like if you have a very specific vision in your head for how you want it to look, well, you're the best person to make it happen. Now it is kind of weird because I made this in JavaScript canvas. So almost all of this is really just me drawing rectangles and lines in the canvas. And I know there are more advanced tools out there like React, but I'm not really familiar with those. And I think even though it would be helpful for my long-term future to learn those, in terms of getting a minimum viable product out in less than 4 days, I'm not gonna try to learn something entirely new. If something has worked in the past for me, I'm just gonna stick with it. And really, the only goal of doing all of this is to get the concept in more people's heads. Like, the people watching this who are just interested in the math and the speed cubing would be like, oh, I never thought about doing it that way, but now I can see it gets you a lot of information. And so the other speed cubers who are watching this might build their own tools that are more mobile friendly, or maybe are able to connect to the internet. And I totally welcome people to do that, to sort of build a much better version of this tool than I ever could. Just credit me for the original idea, of course. Or maybe nobody cares about this idea enough to do anything, and that's all right too. This is already enough for me to be pretty proud of, and it has all the baseline features that I think a tool like this should have. Yeah, so if you want to check out the source code, the GitHub link is in the description.
Part 11. Is this video too long?
And one last thing I wanted to discuss is that some viewers might think, oh, if you had to make a 20-minute video to explain how your tool works, then it's clearly not very beginner-friendly or self-explanatory. And in response to that, I would say that this video is not meant to be the most accessible, clean, cut and packaged explanation, because it's sort of like the debut of this whole concept at all. I'm explaining these features in as much detail to sort of fully get the idea in any other developer's head on how to do this, right? So if someone else out there wants to make like a 2-minute video that has all the bells and whistles removed and just explains how to use this tool and what it means in as quickly as possible and as beginner friendly as possible, go for it. That's not what this video is for, so I think the more things there are on the internet, the better. I think that in terms of my work on this project, I'm essentially done. I'm not going to be doing anything more. Thank you for watching. Goodbye.